end and head of the Center for Market Studies, Spatial Economics. And it is my pleasure and honor to introduce him as a speaker. I should say that about his great way in science that he performed. Jacques was working in core Center for Operation Research and Economics within Louvain University in Belgium, near Brussels. He was working also in Paris School of Economics and helped Lafon, right, to develop it. So he's an organizer also, not only a very well-known scientist. Then Jacques returned to Core Center Operation Research and Economics to Belgium, becoming at some point a director of it and also developed. So Jacques, as organizer of science, is as well known in Europe as a scientist. If speaking about science, he remains for many years among top 1% of economists in the world most cited. And also I would say, if you look on REPEC side, among all economists affiliated with Russian universities, he is #1. Okay, to microphone I will. Jacques is #1. The second is Eric Maskin, the Nobel Prize winner, and several other well-known foreigners. And it is our luck to invite and interact for collaboration such important people as Eric Maskin and Jacques Thies. I would say about the scientific part, why we know Jacques and why he's so well cited. He was working in several areas, including industrial organization, and probably many of us know the paper by Jacques and Gabsevich extending the hoteling model to another dimension. Also, Jacques worked in discrete choice theory, and many people who work with modern empirical I/O know the book by Anderson, De Palma, and Jacques Thies, The Discrete Choice, putting together the findings known by McFadden first, and then this is a well-known book on discrete choice theory, which now becomes the most important part of empirical I/O. And thirdly, the third field is the international trade and economic geography, for which Jacques has several books together with Combs, and with Fujita-san, and they are very well known, and the kind of models, Jacques, maybe I should not tell the essence of the model, but these are modern economic geography based on a theory of monopolistic competition, which burst out after Krugman and little by little conquered the areas of international trade, economic geography, macroeconomics to some extent. And Jacques is also a scientist in general market theory, which is not applied by general market theory. What is the market per se? How supply and demand, how we should think about supply and demand, how is it balanced? And the latest papers, including him and Philippe Uschev, tell about the most general market models which are available at this moment. So I should stop here and say hello to Jacques, that we are very happy to have, and you have an hour and a half. Thank you.
So, hello everybody. Thank you for coming. It's a great privilege for me to be here this afternoon. It's not the first time I'm in Russia, as Sergei told you, right? I mean, I'm often in Russia, but not in Moscow, right? Because I'm a St. Petersburg lover, to tell you the truth. not that I dislike Moscow, but you know, the two cities are very different, and I'm a city guy. So what I like in St. Petersburg, you know, I can walk easily, right? Buildings are wonderful. Food is very nice. This is the kind of stuff which I really enjoy when I'm in a city. So this will be the topic of my talk. It's a little bit daring, right? Because the origin of cities is something difficult. But you should keep in mind that we have the word about, right? Or on. Right? So it means that we are going to talk about it. But doesn't mean that we will learn that you will learn everything about cities, the origin of cities, right? Because it's a very complicated problem. Now, since I have a bit of time, I would like to give you a bit of the background of this paper. I met Yorgos Papayoglou. He's Greek, but he's professor in Canada. In 1979, 40 years ago, many of you were not born. Many of you were not born. And Yorgos told me, but Jacques, you are interested in location problem and so on and so forth, but you know, the main issue is, why do we have cities? And I look at him and say, is it not obvious? He said, tell me what's the explanation. Then say, okay, we have cities, but it's not the end of the story, right? We have huge cities. Think of Tokyo, the metro, when I mean cities, I mean the economic agglomeration, right? When I mention Moscow, I don't mention the city, but again, the economic agglomeration. Tokyo is a bit more than 30 million people today. So why do so many people decide to live together? New York City is 18 million. You have in Africa a city like Kinshasa, which is about 20 million people. Right? Not as prosperous, of course, as Tokyo and New York City, but still huge. Moscow is the biggest metropolitan area of Europe, right? Before London and Paris. And we have only 3 of them, right? In Europe. Only 3 big cities. Now, should we care about that? And the answer is yes, we should care about it, because if you take the United States, for which we have good data, why do I mention the United States? Because, you know, if you want to compare Moscow or Paris, the difficulty is that the data are not obtained in the same way. Where do we determine where is the border of Moscow? Where is the border of Paris? And how do you count the workers and this kind of stuff? So when you have data from the same country, then you apply the same rules. Right? And so the Americans understood long ago that the metropolitan area is much bigger than the city. And they collect data about metropolitan areas. And actually, when you look at the 20 top cities in the US, they produce half of the US GDP. Okay? About 50% of the American GDP is produced in 20 big cities. Now, you take the United States, it's not as big as Russia, but still it's fairly big, especially compared to Belgium. It's fairly big, and you have 20 dots. Well, some of them, of course, New York City, Philadelphia, on the other side, LA, San Francisco, then you have Chicago, then you go to St. Louis, then you go to Texas, and very quickly you get them all. On top of it, when you look where, not all of them, but when you look at the top universities are, not all, but many of them are also located in big cities. Of course, they are counterexample. Cornell is located in the middle of nowhere, right? But otherwise, Cornell, by the way, has a hospital, and the hospital is located in New York City, right? It's not located where the campus is. So we want to understand why we have these big cities, why people choose to live there. I was explained last week that if you rent a place in Moscow for something comparable in St. Petersburg, it's about twice as much here than in St. Petersburg. So why to pay such high housing costs, right? What's the point? Actually, why not to go to a small places where the cost of living is much cheaper? On top of it, in addition, first time I came to Moscow, I went to Nes, but lived in the city center. I had a long commute by subway, and you have a good subway system, which is not necessarily true everywhere. So I took the subway, it took me 40 minutes. 40 minutes by the end of the day. By Japanese standard, that's nothing, because it's 1 hour and a half in the morning, 1 hour and a half in the afternoon, 3 hours per day, on average. Okay. So someone counted it that in terms of commuting, adding the commuting time of American workers for 1 year, this is the equivalent of 2 million years. 2 million years are waste in commuting. So why to do it, right? It's not fun to be in the subway just like that. In Paris, you can imagine, when it's warm, we are packed like sardines right in a can. It doesn't smell very good either. So why do we do this, right? Why do we have cities? Why not to enjoy the countryside and blah, blah, blah. So that's something we wanted to do with Yogo. And Yogo was trained as an architect. Then he said, if I want to understand something about urbanisms, I should study city planning. He went to Ohio State University, where they had, by the time, a very good school in city planning. Graduated there. So it's not enough. I must understand better geography. So he studied economic geography, but the old one. And then he said, well, geography is not enough. I should learn economics. So you can imagine, right? As an architect, he became an economist. He has papers in Econometrica, American Economic Review, Journal of Economic Theory, which is not too bad for an architect, right? So we start working together on something that the geographers like, which is the interaction between distributions. You have a distribution of a certain type of people. You have another distribution, and those people interact. That's the way geographers look at, the special issues. You may have a third group, and so on and so forth. Now, what is a good place for me? Right? And this is the essence of special economics. What is the best place for me? Depends on where you are. Why? First of all, for the reason I said before, in the countryside, we may enjoy a lot of space. So we like more space than less space. I guess we agree on that. But we are social animals. We like to interact with other people. Right? Now, interacting with people, of course, especially in the old days, but even today, it's easier when we are close to each other. If we are far from each other, of course, we can use internet. We do it, we use internet, but at some point, we come to some issues which are a bit difficult and say, we should meet, right? Just to give you a personal example. When Masa Fujita and I Masa Japan, wrote a book together, we exchanged files by email. And we agree, here we disagree. Now, with Japanese friend, you have to be extremely polite. You just say, no, this is wrong. You just say, maybe it could be better done. Maybe. So, we say, okay, let's put this aside. Number one. Then, second source of disagreement. Third disagreement. So we had a couple of pages of disagreement. So what do we do now? Let's meet. Okay, let's meet physically. Where? He loved Paris. Was fine. Went to Paris. We met. Within a day, 1 day, we agree on everything. Everything was settled down, right? Because very quickly, I was able to read, and he read on my face, okay, I see what you mean, fine. And it was this, don't try to do this by mail, right? It's hopeless. Now, you say, well, wait a minute, you use internet a lot. Yes, we do internet a lot. But without our meetings, because we met more than once, there would be no books. And therefore, internet would be useless. we understood very quickly that we had to meet to solve the unsolvable problems. And so we use internet, but we physically met thanks to internet. Without internet, of course, it would have been impossible, but with internet only, it would also have been possible. So we still have to meet. And you see in this case, internet is not a substitute for meeting. It's a complement. They go together. Because we can exchange by internet, we decide to meet. Otherwise, we would not decide to meet. So, Yorgo and I start working by the time, 79 to 80. And we wrote a paper, which was finished in 81. We sent the paper to a journal. The referee said, well, it's well written, because Yorgos writes extremely well. He's an architect, so beauty matters to him. The math are correct. I think I had got some credit for that. But what is this kind of issue? Cities, that's not for economists. It's for urban planners, for geographers. It's not for economists. Fine. So we try a second journal. Exactly the same comment. It's not, this agglomeration. It's not for economists. So we rewrote completely the paper. I'm not going to bother you with that. And eventually we got it published in a very distant journal. But nobody was interested. Economists are zero interested in this kind of issues. Nowadays, in the workshop we organize, Sergei organized here, you see that there is a growing, fast-growing number of young people who work on cities and in spatial economics, but by the time, very few. And then Yorgo said, let's write the second one. And say, no, Yorgo, no, I'm not going to write the second paper, but it's hopeless, right? Nobody's interested. So he started working a bit with André de Palma, who was a friend of mine. André has a PhD in physics, with Prigogine, a Nobel Prize winner. But they stopped. It was too difficult. Now, Yorgo is older than me, which means, I'm already very old, but Yorgo is over 80. And recently he said, Jacques, I would like to go back to this paper. You see, Yorgos. About 40 years ago, we failed. We are not going to solve this problem, right? It's too complicated. You work with André. You didn't solve it either, right? So, Jacques, it's going to be my last paper. Do me a favor. So I returned to the paper. And actually, soon after I came to St. Petersburg and talked to Philippe. Say, Philippe, what about this? We have a problem for those who are familiar. That's a problem in functional analysis. Now, we cannot use the standard technique of finite dimensional spaces. So we better know some theorems, which not all theorems can be extended from a finite dimensional space to an infinite dimensional space. We have to be careful, and so on and so forth. So with Philip, we start interacting and working together. And then you have this joint paper, which involved 3 generations of researchers, 3 generations of people. Well, it's unusual. So now, what do we do in this paper? It's a very abstract model, but we believe that this very abstract model may be useful as a benchmark, right, to discuss various issues. And I will try to show you what we mean by that. When you observe the urban system, first things, a hierarchy. Big cities, medium-sized cities, small cities, towns, villages. What do we have this? Second, several geographers, and Kristaller is the most famous name in this field, have observed that there is some regularity in the location of cities. Right? At least when space is more or less homogeneous. I'll come to it in a moment. So can we explain that? As an economist, actually the 4 of us now are economists, we want to start from a featureless space. Why that? Tokyo has a great harbor nearby, Yokohama. London also is a great harbor. New York City, it's obvious. LA, likewise. Moscow is not. Paris is not either. Yes, you have a... Oh, by the way, if you have questions, don't hesitate to interrupt me, right? There are no stupid questions. There are only stupid answers. So feel free to interrupt me as many times as you want. So if you assume there is a port here, then the probability that this place will attract people is higher than if there is no port. So what's the idea here? Is to start with a space which is featureless. It has one location here, one location there. That's exactly the same thing. They are a priori perfectly equivalent. Why do we want to do this? Why do we make this assumption? Because we want to focus on pure mechanisms, social science mechanisms, that may generate cities and an urban hierarchy. Not by assuming, although it's realistic, right? Not by assuming there are natural features that explain, well, natural features may explain why Tokyo is located where it is, but it does not explain why 30 million people live in Tokyo. Okay, this is a very different story. So, now, when you look at the literature, you see there are two types of forces. A bit like in physics, by the way. You have local forces. We don't like congestion, right? You don't like to be stuck in the congestion, the traffic for half an hour, right? In Moscow or in another city, it's not fun. You don't like to be stuck in the elevator with many other people, it's not fun either. And as I said before, we like a bigger place to a smaller place. So, if we like being close to each other, well, close to each other at some distance, but not just there, right? So we have this local force. But as I say, we are social animal. We like interaction with other people, and those interactions may be global. Meaning that we interact with people at a distance, we interact with people who are further away, less, but we'll see how. So for us, we want to focus on the interplay between these two types of forces to figure out when, whether first, and when we may observe the emergence of agglomeration. Okay? So that's very simple stuff. Now, you will see the word central place, which is used in geography to describe the big area. There are central place of order 1, right, with Moscow. And then you have central place of second orders, central place of third orders, and so on and so forth. That's it. So here, this will be just a shorthand to describe the peaks in the distribution. Okay? So this is what we want to do. I already mentioned it, no need. The problem has been extensively studied in the literature by different people. Geography and regional science, people who use spatial competition theory, people who Krugman type new economic geography, in urban economics, and nowadays in spatial quantitative economics. So that's very popular. Nevertheless, you know, it's a difficult problem. It's a difficult problem because very often they are non-convex cities. Now, let me skip that here. Now, when we think about space, how to model space, the first question, which geometry? Now, there is a very nice old papers by Martin Beckman who consider a compact interval. People dislike being close to others locally, and they like to interact. And what's the equilibrium outcome? A bell-shaped curve. So you have a city center, in a way, all right, which is where the bell, the top of the bell is reached. And then as you move away from the center, the population density decreases. Which is what we observe, right? We have a city centers, and usually, not always, it depends on direction, but usually the population density tends to decrease. Problem, if you take the two endpoints of the interval, you move them further and further away, the bell shape tends to collapse. So what I mean? In other words, we get this bell shape because we start with two boundaries. One endpoint here, another one there. And if we move them further and further away, at the limit, you get a flat world. So, in a relatively recent paper, two other people, Bosset and Picard, say, okay, let's work on the circle. Because on the circle, there is no boundaries, right? Let's do that. They get something completely different. First, they get multiplicity of equilibria, like uniqueness, like that. And they may have any odd number. Don't ask me why it is an odd number. So it may be one city, 3 cities, 5 cities, 7 cities, which are equally spaced around the circle. Otherwise, the model is exactly the same. What does it tell us? Well, it tells us something simple but important. The way we model space will generate very specific results. So we have to be careful about what we are going to assume. So what we do, we take the real life. No boundary, nothing. Perfect. One-dimensional, yes. But if you want to, we can talk about it later on. Of course, the world is not one-dimensional. It's obvious. But let's start with something simple first. But it's not necessarily obvious because, you know, when you work on the whole real line, we have a problem of integrability of functions. And on top of it, what we will see is that the equilibrium spatial distribution is a solution to integral equations. Now, integral equations is not something that economists use very often. Fortunately, the Russian people are outstanding in this field. I mean the Russian mathematicians. I'm not talking about the layman or the laywoman. So that's why Philip was a bit familiar. I knew the existence. We knew the existence of integral equation, but none of the three of us knew that there's a handbook published in this country with the solution to 2,100 integral equations. 2,100. You have to be a mathematician, you know, to do something like that. So there was some hope. So let's go to it. So what do we do? As I told you, a local congestion effect, which will depend on how many people are with me here at X. Okay? And I don't want many people to be here with me because this means that I have to share the amount of land. I know at one point it's a zero measure set. I hope you know that I know these things, so I will use it in a simple way. So the amount of space here, if we increase the number of people, there is more and more congestion. Or the price of land would increase. Okay. Now, in the literature, to deal with this, I did that. I'm going to learn something from you. Now, what do we know? We know that distance is an impediment. The greater is the distance, the lower is the probability I learn from you. Right? It's very much like the gravity equation in trade theory. But if this is not learning just from you, but from all of you at the same distance, because there are several people, then the probability will be higher. Right? So it's a gravity effect. So that's why many people use an exponential decay function. It's just something like that. A nice function. We all like this. We know that exponential functions are easy, very friendly, and so on and so forth. So that's why you find it in transportation analysis and in urban economics. They say, okay, let's use that. And let me show you, one comment. We are going to work with these two effects as two external effects. You saw that. You are going to hit the model. Why? Because there is no market. It doesn't mean that we have a planning model, right? We don't have this. We don't have a planning model. It's not a paper for Soviet Union. But we have no explicit market. We use, like in econometry, reduced form which are consistent with different narratives. And I hope to show you a few of them. So let's start with the case in which everything is homogeneous. We have a continuum of identical people, agents, whatever you want, typically individuals. Right? They're all the same. Now, we focus on what? Distribution, densities of population. Right? This density should be non-negative, of course, a negative number of people doesn't make much sense. Piecewise continuous does not match, right? And bounded, I mean, they don't have an infinite number, no Dirac stuff here. Now, because the uniform state, right, is one of the special equilibrium we would like to consider, we have a problem because this function cannot be integrated over the real life. So we focus on functions such that n bar is given to us. We will call it the mean. You take the integral from minus b to plus b, you divide by 2b, and you say the limit of this integral is always finite, n equal to n bar. So it's a subclass of the integral functions. Right? And the mean is always n bar. So in a way, n bar is the population size. Okay? N bar is large, many people. N bar is low, few people. So here is my utility function. E of x is 1. This is the externality. There's the exponential minus the decay effect. The distance between the location x and y. And y is the number of people at y. Okay, it's a density, right? It should be 0, blah, blah, blah. Again, I know this thing, we all know this. So this is the number of people at y. So you see, the distance is an impediment. The larger the distance, the lower is the value of the externality. But the higher the number of people there, the higher is the value of the externality. So this is the gravity effect. And what is beta? Beta precisely measures the obstacle to interactions. While a high value of beta, you know the exponential will be 0 almost everywhere. If beta equals 0, you can interact with people who are almost at infinity. So in a sense, a high value of beta means that transportation costs, communication costs are high. Okay? Are low, excuse me. On the contrary, if beta is very low, that's the opposite. If beta equals 0, that's the opposite. So beta can be viewed as a kind of proxy for the technologies that people can use to communicate. We can ship goods, we can trade goods, we can talk, we can travel. Beta will tell us how difficult it is. And this gives rise to something which is called, in transport analysis, the exponential gravity equations. Whereas in train model, right, this would be here divided by the distance between x and y, because we know that the estimation of the exponent are very close to 1. In other words, you know, in trade theory, as you, on average, you double the distance between two countries, you reduce the intensity of trade by half, on average. Okay? So, in a way, this distance really matters. And now what is this guy here? But if many people are located with me, I'm unhappy. Now what is alpha? Alpha tells me there is a trade-off right here. I would like to be with many people around, but not just here. Now if I care about congestion, I don't care about interaction with the others. Alpha will be very large. But if you have new technologies, and we can build tall buildings, right? When we may have a higher density of people and the same amount of space for each household. because we just keep adding floors. Right? So in this case, technological innovation would mean lower and lower value of alpha. So you see how by playing with the two parameters, alpha and beta, it is possible to tell some stories which are consistent with the main some of the main models of urban economics and economic geography. I told you I have no land, I have no market. Actually, well, I could use a land market by assuming that's utility functions. Right? So Z is the numeraire. This means we have quasi-linear utility functions. The budget constraint is very simple. The indirect utility function is written like that, which is exactly what I had before. So if you insist on having a market, I can introduce a market, and I'll end up with the same expressions here. Okay? So, I already said so. Now, this is microeconomics. In a sense that each one of us choose, it's a Nash equilibrium. Each one of us choose her or his most preferred locations, given the location of the others. Right? Why? Because, as I said before, my best location depends on where you are. And your best locations depends on where the others are. So we have a special, because we are the same, perfectly homogeneous. All of us must reach the same utility level in equilibrium because we are the same. So we have this expression, star is for the equilibrium, when some people are located at X. Because we don't know yet, we could have empty spaces. Now, indeed, if we have nobody at X, that's because the utility level at X is lower than the utility level, the equilibrium utility level. Last, we have this constraint, the population constraint. The mean of the equilibrium distribution must be equal to n bar. First, yes, like in many models, the uniform distribution is always a special equilibrium. And what we want to do, given that, is to say, okay, when do we move away from this uniform distribution? Okay. Second, oops, and that's not easy to do, right? The special equilibrium involves no empty space. There could be a zero measure set, blah, 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 but no intervals which are empty. Yes? No, the real line. Oops, here's the definition. Take n bar here, you factorize it to b divided by 2b. Was it your question? There was a question. Okay? So it works. It was the simple trick. That's what you didn't think about it with you almost 40 years ago. Okay? This time I thought about it. Last, you can show that we focus on piecewise continuous. We can show that the equilibrium is continuous. Your question?
Why can there be no unpopular areas?
Excuse me, I didn't hear your questions.
Why can't there be no unpopular areas? Why is it not possible to have unpopular areas?
We prove it. It requires, it's a fairly long proof with lemma. We don't have a great economic intuition for it, and I cannot really answer. I cannot answer your question in a simple way. The mathematical proof is fairly involved. The idea is actually, if you have, roughly speaking, if you have an empty interval, right, you are close to it. So zero interaction with those locations because nobody's there, right? But you are outside, and you have some congestion effect. If you jump a little bit inside, right, no congestion effect at all. But the externality effect doesn't change much. See?
Can it be rationalized by the fact that you have an exponential decay function? Like when you have consumer preferences, you have a logic model then.
I will talk about I will talk about non-exponential functions, at the end of the talk. But true for the proof, we use the explicit form of the exponential functions. And I don't know yet, because we keep working on this, I don't know yet if this is true for any kind of externality functions.
But this also precludes agglomeration.
That's what, sorry?
This also excludes agglomeration.
Why? I could have empty space, then agglomeration, then an empty space, then agglomeration.
I mean, full agglomeration. All functions like
No. That's a full agglomeration would mean that I have a direct distribution where with a mass point. But if I have a mass point, then the congestion effect goes to infinity. So we don't want this, right? So any special equilibrium is a solution to this integral equation, which is a Fredholm second order kind. Why? Because you see what we want to determine, which is the distribution, the density here, is at the right-hand side and the left-hand side. Okay? So that's not too complicated. That's part of it. This is in this handbook, right, where we can use. First propositions. Now, you remember alpha is the weight associated with the congestion effect, and beta measures the independence, the impact of distance on the interaction with people. And this will be a key parameters for us. First, the uniform distribution of individuals is a special equilibrium. It is unique and it is stable if and only if this guy is smaller than 1. To show it, we use Banach's 6-point theorem. Okay? So what does it tell us? It tells us that if alpha is large, we care about congestion very much more than interacting with other people. So we prefer to live in a flat world. In the very, very old days, where we were hunters, right? We need a big amount of land, right, to hunt and find games. It was difficult. So by the time alpha was very high, and the population was very low, we'll come to it in a moment. Beta people did not care very much. We had a small group of people who lived together. Agglomeration was a non-issue. Now, what happens when beta changes? Or, so smaller than 1, it becomes smaller and smaller. So interacting becomes easier and easier. Right? Or we care less. We know how to grow vegetables. So we don't need the same amount of space. We can feed ourselves by using less land. So alpha becomes lower. So we get that. If phi is larger than 1, larger than equal to, it's okay, but at 1, I mean, it's everything works well. Then it's given by this expression. The average plus, okay, it's a constant. I come to it later on. And it's a sinus, which means what? I get something like that. Now, what does it say? Why do I have 3? Why do I have a blue? Why do I have a red? And so on and so forth. Because here, you see I have this constant. This constant, I don't know. Is it 0, 1? Is it 5? I don't know yet. So, a priori, we have a continuum of equilibria. R cannot be too large. The sinus can be -1. So I have n bar minus A. Again, it cannot be negative. So the upper bound admissible value for A is n bar. Right? But is it 0? If it is 0, I'm back to the uniform state. But it could be something between 0 and n bar. So this is what we have, right? The blue line is the case when A equal n bar. Now, here I have a lower value of A, and the red one, the value of A, is even smaller. But, what does it show us, which we like? Then you have a periodic distributions of this pattern here over the whole real line. I come to T in a moment, but what does it tell us here? You see, this would be, I can choose the 0 whenever I want because it's the real line. No boundaries. So, it doesn't matter where 0 is. So here you see the population density take its highest value. At this point, people do not consume much land. There's a strong congestion effect. But they interact with a lot of people who are located nearby. And they can still interact with some people who are there and even further away. But the amount of interaction gets smaller and smaller and smaller. Right? But what is important is this kind of local interaction because there are many people around. And then you get here in this kind of cities, you get something in which the distribution of the population is bell-shaped, which is what we would like to find. Something like a city center. And then the population decreases as you move away from the city center. Now, what is the T here? Right? Well, the value of T is that, right? It's the period of the system. We depend on phi. You see, I need phi to be larger than 1, or I'm in trouble. Here I get the parameters beta. So, what is critical for us here is that the population of each city, which is given by that, this is one city, is n bar times T. So n bar is given. If n bar increases, more people, you get a bigger city. But the physical size of the city, T, here, this interval, does not change because n bar does not enter T. Okay? Now, what does it say, this T, when you study that, right? Phi is here, beta is there. Well, T between, there's distance between two cities increases when alpha gets smaller and smaller, when local congestion matters less and less to you. In other words, you are going to, you are going to have here wider and wider cities, and you can interact a lot with those people who are located close to you, because you care less about the local congestion effect. If you care more, the cities become smaller. Okay? Now, what's the impact of beta? Beta measures the cost of interacting, in a sense, with the other people. So, increasing or decreasing beta should have always the same impact. And the not always, it should be monotone. And the answer is no. The impact of beta on T is U-shaped, in the sense that when you decrease the value of beta, when let's say we put it here, communication or transportation cost decreases, then T expands, and then it shrinks. It's not monotone. Why is it like that? Beta, gets better and better for you. It gets smaller and smaller. So at the beginning, you interact with more and more people. But at some point, there are so many people around that the congestion effect becomes stronger, overcome the interaction effect, and since beta keeps decreasing, in any case, it's easy to interact with the neighboring city and with the neighbors of the neighboring cities. So we don't have a monotone relationship now. When you look at the work of Krugman, Venables, and other people in New Economic Geography, when you look at the impact of trade costs, what do you observe? First, a uniform state for high transportation costs. Then, when transportation costs decrease, you get agglomeration. But when transportation costs decrease even further, then you get again some redispersion. Why? Because the wage in the agglomeration is so high that some firm prefers to go to the periphery where wages are very low. Okay? Similar ideas to what we have here. Now, A continuum of equilibrium, we don't like that. So, can we show something? Well, it's the usual stuff, right? We are going to focus on the stable equilibrium. Now, the idea of stability here, don't think of a very sophisticated mathematical concept. We just shake a little bit the distribution locally. Do we return to the initial distributions, right? So, yes, when A is smaller than n bar, they are unstable. By contrast, when A equal n bar, it is stable. In other words, the equilibrium we can focus on is the blue line. We have big cities, okay? But they all have the same size. But it's already something. We observe that for low value of alpha or beta, so when the interaction becomes easier, when congestion matters less, then there will be economic agglomeration. Cities will emerge. Welfare. Okay. The welfare level is given by this very simple expressions. Look at this one. You see n bar is there. We have two cases, phi smaller than 1, phi larger than 1. Okay. Assume that phi is smaller than 1. This is negative. So if the population increases, it's bad news. Of course, the congestion effect dominates. So if you bring more people, I mean, people are less happy. But when phi cross the value 1 from below, then we get urbanization, we get cities. But then you can have more people. People get better off when the population grows. So you see, when the technologies, the social relationships are such that people don't like to interact and we have a flat world, we should have a low populations. But when the technologies get developed enough for the congestion effect to be weaker and the interaction effect to be stronger, having more people is a good news. Still, right, we don't have hierarchy. We don't have very big and very small cities. So what do? Let's consider two populations. That's already becomes a bit more complicated, right? Because here you interact with your own people, JJ, but you also interact with the other people of the other population. Maybe you don't want to, right? Here you might have in the US people like Trump who don't like to be with the black people, and they never interact with the black people. Or you might have some Islamists here, and they never want to interact with the non-Muslim people. Whatever, you can have a lot of stories like that, right? About segregation. Now, we still have here the fact that we are going to share space with our people, but are you willing to, okay, think the young people, they make a lot of music during the night, they have parties. Someone of my age prefer a quiet place, right? So falling asleep, that's more difficult. As a result, being with a lot of young people is not a great news to me, right? Locally. So this coefficient is high, whereas this one is small for me. So you have different possibilities. So in a general, just me give you a simple story. We are consumers. The other populations, firms. Now, we are attracted by places where there are many firms. Why? Because there is more competition. So price should be lower. There should be more variety. So more choice, we are better. It's a good news. Now, firms. Firms are attracted by places where there is a big market, where there are many people. Okay? So we know the sign of this alpha. Now, the within our group, the within effect. Well, I don't like to be with many consumers because we compute for land. And firms don't like to be with other firms because local competition gets tougher and tougher. And firms don't like that. So, you know, we can make sensible assumptions about the sign of the coefficient for this kind of interpretation. Now we have, it's a bit more complicated. It's a system of two integral equations, right? In which we have within effect, within each population, a between effect between the two populations. So you see the number of parameters I have here, right? So j equal 1 and 2, j equal k, or j is different from k, whatever you want. So what can we say? Well, we can say something about the utility level. All right. The equilibrium utility level. You see, it depends on the size of the two populations. For example, assume I'm a racist from Alabama, right, in the south of the United States. I belong to this group. This is negative to me. I don't want black people to be near my place. If you bring more and more black people nearby, I'm less and less happy. I'm an anti-racist. I like being with other people. I like mixing. This is positive. So if there are more people from the other population, I'm happier. So, you know, we can capture different types of social attitudes between the two groups. Now, we don't like to look at all possible cases, right? There are many of them. So, first things, we have a theorem. Okay, we build a matrix, right? Here, Philip was great to figure out how to find this matrix, which depend on the parameters. We have many parameters. We have 8. Actually, we can normalize 1 to 1. We have 7 parameters. Before we had 2, sorry. Now we have 7 of them. So we have this matrix, and you can prove it here, the following result. If this matrix, I'm sure that everybody have heard of this kind of stuff, has no negative eigenvalues, well, real eigenvalues, so we have a flat world. It's the unique equilibrium. Now, what does it mean? I will show you example. If there is only one real eigenvalues, we get something very similar to what we observed before. Okay, if you remember that. Oops. Sorry, I should have. That's one. It is very, very similar. Actually, it is the same. Except that now I have two constants, A1 and A2. If I have at least 2 eigenvalues, which are negative, then I get a sin, and a sin here, but look, the 2 lambda are different. So the maximum of this one is not at the same point as the maximum of that one. So now when I take the sum of these two signers, the maximum can be at some point. I have another one, I get a world, for example, like this one. Okay, this is great. Look, there's this crystal air who tell us you have big cities. And you see these big cities is formed by mainly blue people and a few red people. Now, there's no race, right? Blue and red, I'm fine. Then the other cities get smaller and smaller as you move away. And you see we're in a world, of course, where we have more blue people than red people. Okay? That's the outcome of the simulation. Turns out that it was the first simulation. It's great, because it looks exactly like this kind of hierarchy that we would observe in a perfectly symmetric setting. Let's change the parameters a little bit. A very different story. What do we get here? You see, 1, 2, 3, 4, 5 very big cities. Does it make any sense? Well, think of Germany. They have what they call the Big Five: Berlin, Hamburg, Frankfurt, Cologne, Munich. about the same size. So I would be the last to say that this represents the German economy, right? But it could be that an economy has 5 top cities. There's nothing stupid in that. So between this and that, you know, well, we get hierarchy because you see that we have smaller cities. Look, this one is very small. This one is a medium-sized city. This is a big city. Okay? We have this urban hierarchy, so that's fine. But here we have it, it's obvious. But we would like to know a bit more. So let's make assumptions, right? Here, we are the same in the two groups about the congestion effect. And we don't care about the others. Here, same thing. We like to interact within our group, and we also like to interact with the others, but less. Mathematicians like to talk with mathematicians. They also like to talk to physicists, but less. Physicists like to talk to physicists. They also like to talk to mathematicians, but less. Okay? That's it. Now, look at this proposition. Our phi is the same as before, because now we have only one alpha and one beta, but we have also gamma, a third parameter. So we have 3. So again, if phi, which is the same as before, 1 over 2 over alpha beta, if it is small enough, then the flat world is the only stable equilibrium. Okay? It's the only equilibrium and it is stable. But now I have gamma here, right? Which is strictly positive. Before I didn't have this gamma, it was 0. No interaction with the others, because there was only one population. So now I have this case with these 2 intermediate values, which tell us that we have central place, but again, it's going to be like that, equally distant. Now, if we phi become large enough, then we have central place of different sizes. We get hierarchy. And this is exactly what we observe in these cases. When you look at the value, this is what we can obtain. You can do a lot of simulation and get something like that when we assume that the congestion effect is not too strong and the interaction effect becomes stronger and stronger. Okay? So here we need 2 populations to get this urban hierarchy, and 1 population is enough to get the emergence of economic agglomeration. But what about the exponential decay functions? Well, let's assume something more general, an unspecified externality functions, right? Where g is a decreasing function of distance and is the same, but before it was just the exponential. Example, you could have something like that, right? You interact with people within a certain distance in your neighborhood. Outside the neighborhood, you say, no, it's too far away, I don't go there. I'm not interested. It could be linear decreasing, but then it becomes negative. So it's also implied that, you know, you have some interval. Well, the exponential, the negative exponential, or the Gaussian distribution also does the job. Now, can we show some result? Let me show you this. This is the integral of function g. Right? So if this guy, is small enough, so if the potential of interactions, how much we value interactions, if it is small enough, we are back to our first proposition. The flat world is the only stable equilibrium. Right? Again, that's because for this general specification, this function g is whatever you want, okay? Decreasing, that's it. Then, if it takes low values, the integral is small, and therefore the congestion effect alpha is large, you get a flat world. Now, what about the others? Well, we're still working on it, but what will be the economic intuition of this? we have to take the Fourier transformation, the transform of the transformation, I don't know which one to say, of the G function of the external. And then you see again now, if the externality effect is strong enough compared to the congestion effect, and if this guy is single peak, we don't know yet what it means, right? Don't ask me. It's work in progress. Then we get something like that, which is again periodical, like our proposition 2. But if this function is not single peak, we get cos and sin here. And again, with a single population, we may obtain a hierarchy. In other words, how we specify the special externality function matters for the result. Everybody uses an exponential because it seems it's easy, it is intuitive, and nobody questions it. Well, unfortunately, it may matter for the result. We'll see. I think it's already late. So, conclusion. Although we have an extremely simple model, very, very simple model, we can already get many different urban patterns. So if you have a complicated model, you can imagine what we're going to obtain, right? We obtain two results which are not necessarily easy to prove, because if you look at the work of my friend Vernon Henderson, right, he has cities of different size, but those cities are like floating islands. I mean that there are zero transport costs between cities. I produce good 1, you produce good 2, they can be freely traded between us. Doesn't cost anything. So is the distance between us big or small? We just don't know. So that's why these cities are here. The special interaction functions really depends on the distance between the functions. So we know where things are. And we also get some regularity, something stressed by some geographers. And last, that's more for geographers here, for some geographers, the Christaller-Loesch model, according to which you have urban primacy with the top cities, and then we would observe maybe 2 smaller cities, and then 4 even smaller cities, and 8 maybe so, which is something that Christaller observed more or less in southern Germany. Loesch went to the United States before World War II. It was to Wisconsin, because they say it's almost an homogeneous space, it's flat, it's everything. I observed more or less something like that. Equally spaced, more or less equally spaced. Then we can reproduce this kind of stuff. For sure, right? We have used a very simple model. We have to go much further away, but at least I hope that I managed to show you that we can develop some intuition about what the key forces are. That as it becomes easier and easier to interact, the first reaction would be to say, oh, space does not matter. Why should we care about where you are? Because it's easier and cheaper to interact. Internet. So internet is the end of cities. No. It's not that simple. Thank you very much.
Any questions?
Yes.
Possibly your picture with which you interpreted as hierarchy with this
This one?
the previous one, yes.
This one.
This is not strictly hierarchy.
Strictly what?
It's not strictly hierarchy because you do not have this large cities, smaller cities, towns, villages, because the density does not go to 0.
No, you're right. Here, no, you're right. Here we have smaller cities, and again bigger, and then smaller. Yeah, you're absolutely right. You're absolutely right. I agree. Here we get some smaller cities, And actually, you see the smaller cities tends to become bigger here. But the bigger city, as we move away from the biggest one, the size decreases. So it's not exactly crystal average. I agree with you. I agree. They are mixed. The small and the big are mixed. So, some people here talk about, use the expression, you are in the shade of a big city. Therefore, for this small city, I'm sure they are 200 kilometers away from Moscow. There are some small cities, right? I've been to Suzdal, this kind of place. So it's not that far, but it's very small. So what happens? Because the big cities are very big, the small city, they are in the shade. They cannot grow. The other one is just too big for them to grow. Between Chicago and St. Louis, you have smaller cities too. But they cannot compete either with Chicago, they are too close to Chicago, or with St. Louis, they are too close to us. So that's a bit of something like that. Right? But of course, I mean, it's not, it's just an example. We have to be careful, right? It's the outcome of a few simulations. We have to be careful with that. Did I answer your question?
Maybe
Yes.
a question, like you assume that urban costs are only incurred at your own location, right?
Yeah, yeah.
And why not assume spatial decay there as well? It seems a bit arbitrary, right? To say that urban costs are only incurred at your location while interactions, benefits are based on the spatial decay. It could be as well that it's the same function with a different decay, or maybe even the same decay, right?
Okay, three answers. First, this is what people assume in urban economics. The amount of space you consume at a specific location, and this is what we assume in our grid cycle. Okay. Second question, it's a kind of mathematical function. It's not easy because if I'm located here at x, you take an interval, but then you are epsilon away. You have another interval there. So you get many intervals that overlaps. So this makes the problem difficult like that. Third, we start working on a specification of the externality function in which there is something like that. We'll see what, but we start with no result so far. Yes?
Just a note, actually. So in many countries, in many big cities, governments are concerned with the congestion problem. And they try to solve this problem because they feel it is a problem.
Микрофон возьмите, вот нажмите и скажите микрофон. Все, что вы сейчас говорите.
Okay. So I would then take a seat. Okay, so
Yeah, congestion is a problem.
so again,
in
so
many
for
cities.
most governments, congestion is a problem, and they feel like that. So according to your model, the more tolerant people are, the bigger are the cities, right? So am I right that one of the ways to solve the problem of congestion is to decrease the tolerance of people in the cities?
Okay. There are different replies. First, when we had elevators, then, for example, in London, the first floor was usually for shops. In French, we have a word for the second floor. The noble floor was the nicest one, because you have just one staircase. Then you had second, third one, fourth one. There was some form of social discrimination. In other words, as you went up and up, the income decreased. Now, what happened in London when they installed the first elevator? The price of the apartment, first, second floor for you, was high, lower, even lower. Was the other way around. The price at the top floor was the highest. Why? Because you have a nice view. And the one on the second floor for you went down because you are close to the street. Right? There is too much noise. You don't have a view. And with the elevator, it's just easy to move within the building. So that's the beginning. That's one answer. The second answer is the development of the different transportation means, right? If you look at the history of cities, it is truly amazing how the subway and then cars have a huge, huge impact on the development of cities and the size of cities. Now, there is someone who presented a paper today, I guess, about if we have these automatic cars, right? Will people commute more or less? If we can share the car, because we are no longer the owner of the car. They are like minibuses, in a sense, these cars, right? So you and I are not the owners of the car. We can share it. We reduce congestion. Fourth, we have something that economists like, road pricing. Right? This is implemented in Singapore in a very nice way. This is also implemented in London, but it's not terribly well done. This is also done in Stockholm. The interesting point is that people hate road pricing. They are willing to pay for many things, but if you tell people you are going to pay that much when you drive at 6 p.m., they will vote for anybody else, say, let's get rid of it. People hate that. That's true. And you know, it is an issue because on average, cars are used 5% of the time. In other words, on average, cars are parked and immobile 95% of the time. So we have a problem around 6, between 5 and 7, and we have a problem in the morning. So for us, road pricing makes sense. Politically, very difficult. So we have this endless debate, should we build more subway or not? I mean, it's, we probably, I mean, when I talk to my friend in transportation economics, because it's really a difficult problem, we probably need some road pricing, we need more transportation, mass transportation, but mass transportation, because there is a project in Paris called the Express Railway, right, which is the new subway around Paris and also that cross Paris. The budget is 30 billion euro, so it's not a small, a small project. It's an automatic railway, and we found out that what is the most important criteria for people is the reliability. The subway will be there at 5:06, not at 5:07. This is what people matters, because they know that they have to be there at 5:05, 5:06. And if you know Tokyo, there are lanes. Right? And I tell you, if you take these lanes, it will take you 1 minute to go to the platform. And the next one, if you cannot walk fast enough, it will take you 3 minutes. So you can compute using your cell phone. The train will arrive in 4 minutes, so I can afford to work a bit slower. The train is going to be here in 1 minute and 30 seconds. I better rush. Okay? And you see how the Japanese people, because the transportation system in Tokyo, the public transport, the mass transportation system in Tokyo is absolutely amazing. Because don't forget, they have earthquake. Japan has a quarter of the earthquake in the world. So they have earthquake very often. And despite of that, the system is extremely efficient. So we have something to learn from them. But it's a difficult problem. It's a very difficult problem.
Probably Jacques can be tired already. We can thank him and have a discussion in Midwest. Thank everybody and thanks Jacques a lot for the lecture. Thank you.